All right, welcome back. So we ended up with the Q number format, and now we want to go like one step further and think about, how do we deal with Q number format, and how do we deal with numbers in different scaling factors, say a Q78 and a Q87. All right, so let's look at adding. All right. So what I love about fixed point numbers is it brings us back to grade school. It brings us back to, when life was much easier. You played on the playground, and you dealt with just learning how to add. So we got to do it again. Add and revisit it. So how do we add numbers of different formats? Well, we do it the same way as in base 10. All right. Make sure the decimals line up. All right, you have to make sure the decimal points line up. What if they don't? Well, we got to fix it. Now, there's only there's only one way to do it. All right, you've got to bit shift one of the numbers to either increase or decrease the number of fraction bits. All right, there's no way around this. All right, this means that one operand is either going to gain a bit of precision or one has to lose it. All right. And what this means is you may have the truncation. You're going to have to either gain a bit or get rid of it. So this also means that the highest bit may be shifted to the left and maybe non-zero, and you may have an overflow. You got to look at the operands and say, if we add these two together, are we going to overflow? Now, even when you line up, you may still have the overflow if the operands are large, so you better be adding into a data type that can handle it. All right? So you think about a Q78 or an 87. The 78 either has to become an 87 or the 87 must become a 78 for it to work. Now, here is the problem, is that if you move the 87 down, what happens is if the 8th bit is set here, you just lost it. All right? All right, that's essentially like an overflow. That is a horrible problem to have. So if that 8th bit is set, you don't want to do that. It's almost universally better to lose this bit and go down to 7 and go to 8. All right. Now you can go this way, 8 the a whole number part down, as long as this 8th bit isn't set. All right. Now, what's interesting in FPGA, lining up decimals is actually easy because you can control wires. You're not working with 16 or 32-bit data. You're working with raw wires. So lining up decimal points is a wire alignment issue and less of a bit shift issue. But keep this in mind: if you have adding two numbers on different scales, you can have this issue. So if you want to multiply the Q numbers, and if it's the same n.n format, it's just like when we first started looking at fixed point numbers. Just do the multiply. It's just you have an extra factor of n. You have this n squared term, so you got to divide by n to get back to qm.n. So the other way here's another interpretation, is that when you multiply numbers, you essentially end up with more precision than you started with, and you got to divide it out. So a Q 7.8 and a Q 7.8, well, even so we have 8 bits, and that's 256 scale factor 256. Multiplying those, we add these numbers here, we get 65K bits, or I'm sorry, a factor of 65,536, 2 to the 16th. We get more precision. We get a Q 15.16 number. All right. So after we do the multiply, we just need the bit shift to the right to divide by 8 to get back to Q 7.8. Now, your intermediate result always requires more bits than your operand. So, for example, a 16 by 16, we need at least 32 to handle that. Now, in this case, if this is a 32-bit, 16 and a 16, we need an intermediate 32-bit number to deal with that. So if we had a 32-bit number and a 32-bit number, we need a 64-bit intermediate, 64-bit intermediate variable to store that result. All right, so the code, and let's look at the pseudocode. We have a short A, a short B. So remember, this is signed. And I'm just going to say this is 7.8, 7.8. I'm going to store in a long, this 32-bit long, my pseudocode, this temporary variable, and that's going to be a Q15.16. All right. So how do you deal with it? It's as simple as this: take A times B. All right. The result is Q15.16, and then we're going to bit shift this result back by 8. That's dividing by that scale factor, because we have a scale factor squared, to get back to our original number. Simple as that. All right, so what if we want to multiply numbers of different Q? So the only thing we really need to start doing first is thinking about the end portion. That's where I like to start. So let's go back to our original, this distributive equation. Now, I've written it a little bit different. Instead of like numbers in front of here, is if we have n values, like the fractional values, I have an n1 and an n2. Well, to get the scale factor is really 2 to the n, because we're using binary scaling. So if we have 8 bits here, the scale factor is 2 to the 8, which is 256. So when we multiply, we have 2 to the n, 1, 2 to the n2 times our multiply. So we have this multiplied together. Remember, when we multiply exponents, so we just add n1 plus n2. So in the Qm.n is that what happens is when we multiply them, we add together the different n values, the number of fractional bits. The m values also get added together. Then we have an extra factor of 1 in there from the multiply, and we have our sign bit. So here is the big statement. After multiplication, you got to decide, what do you want to do with the data? Do you want it in the original format of Q87 or 7.8? Well, here's the key, is you don't have to go back to the original formats if you don't want to. We can actually leave an intermediate result. So in this case, a Q78 and 87. All right, so 8 plus 7 will have, all right, 15 bits there. All right, the dot. 7 plus 8 plus this 1 is 16. All right, so we have a Q16.15. That's a result when we multiply of different Q. All right, so you just got to keep track in your signal processing routine of what that means. All right, so let's look at some tricksy things we can do here. I got some more pseudocode. So let's say we have two 16-bit numbers, A and B, and we're just going to assume A is in 8.7, B is in 7.8, and I have a C for the result, and this C temp is an intermediate. So the first thing we do is we take A times B. The result has 7 plus 8 bits of fraction, so we have a Q16.15. Now, we have to decide how we want to rescale. Now, we can bit shift. We can do whatever we want. So if we bit shift back by 7, we can subtract off 7 of these fractional bits. All right? So 15 minus 7 is Q7.8. We could go back by 8 bits and end up with 7 bits. We could rescale all the way, to Q11.4. And I give a warning here, is that whenever you're shifting to the right, you're truncating fractional bits. So you got to think, how much precision do you want to retain? All right? And that's completely up to you in your application. So this is a little bit higher or a little bit more in-depth topic, but I'll go over it quickly. So because after you do a multiply, you end up with more bits of precision, you got to decide what to do with those bits of precision. You can immediately rescale back to some other format and throw away those extra bits, or you could keep them. Now, whenever we do DSP or signal processing, if signal processing always involves successive operations, all right? Successive operations. So if we're going to do that, why not just leave intermediate terms in their higher precision format, and leave it there until you actually need the lower precision. This is actually a big deal in doing filters. Whenever you do like a digital filter, we want to avoid any error in the intermediate calculation. So why not use the higher precision result until we don't need it anymore, until we absolutely don't need it. So I'm going to look at an FIR filter. This is kind of like a pseudo FIR. This is not, wouldn't definitely be like a real-time implementation, but it's enough pseudocode so you can understand it. So here's the example. I'm going to have a Q7.8 format for an input signal. All right. And I'm assuming this is some circular buffer and some other code's handling this. All right. And all FIR filters need filter coefficients. All right. So I have a Q7.8 for filter coefficients. Now, it turns out in FIR, this is actually a poor choice to do 7.8, but I'm going to do it just because we've been looking at this the whole time in the videos. So here's what we can do, is that in our pseudocode, here's our input signal, filter coefficient. I have an accumulator, and you noticed I put it in 1516 result because we're going to do a multiply. We need higher precision, so this would be like a 32-bit number, and this result. So this retains the full precision in the intermediate computation. So I'm going to make the assumption here that the input signal has the most recent sample at index 0, and index 1 is the previous. We're not going to worry about how that's managed. We're just looking at the core computation. So for an FIR filter, you simply take each one, the input signal and its time history, multiplied by the filter coefficient. So all I'm doing is looping through the 16 samples of my current sample plus time history and my filter coefficients, and I do the multiply. And what I'm doing is after every multiply, I'm simply adding it to this accumulator, all right? Because that's what we do for an FIR filter. But you notice I don't do the bit shift after every multiply because I don't have to. Why rescale back to a 8-bit or 8 bits of precision? Let's leave all that precision to get a more precise result. So what I do is I skip that intermediate, in the intermediate stage here, the rescaling to keep a higher precision result. All right. Then what I do is my final result for this cycle, for just this sample, is I'm going to scale back to Q7.8. Now, let's think about this. We had 16 bits of precision, and we went to 8. Whenever you shift back by 8, what we're essentially doing, if, let me draw this out here. So I just really quickly drew 16 like little ticks here. These are like bits in the fractional part. Whenever you rescale by 8, what we're essentially doing, let's see, did I get them all? Is we're just blowing away those lowest 8 bits. Now, it turns out that is not the most precise way of doing it. Because think about it, if these bits, if you look at What happens is if they're all zeros, we don't care. But let's say this was a value of 1, 0, 0, 0. Let's draw a bunch more zeros. Blowing that away, there's data there. What we should actually be doing is rounding. And here's the base 10 equivalent. Let's say if I had a number 1.274. And let's say this is our high precision, and let's say I just wanted this result. Well, I'm sorry. Let me recircle that here. Let's say I just wanted this result here. Well, I could just take that result directly, 1.2. Well, look at this. We kind of got rid of the 74. Why not round it? Round it up to 1.3. That is technically a more precise representation. All right. So how do we do rounding? Well, it turns out rounding is pretty easy. All right. Now, I'm going to try to say this slowly because this can get kind of confusing. In the last example, we looked at chopping off the lowest 8 bits. Now, to improve the result, we can round the higher precision form before we shift. All right? Rounding is simple. Here's what we need to do. We just have to add a magic value. We have to add 1/2 of the smallest value that the lower precision format can reduce to this higher precision format. This will always generate a number in the higher precision form that will correctly round. So for example, if we're working in Q78 and our intermediate higher precision is Q15.16, what we do is we take the smallest number we can represent in Q78, which is 1/2 and here I just drew it out in binary. Take half of that, which is 1/256. All right. And what I did is I drew it all in binary. It's the same number, except that, let me just see if I can draw this. We shift over that 1 by 1 bit to the right. We divide by 2. The smallest number I can do is, just trying to highlight these here, is I can have 7 zeros and a 1, all right? What I need to do is if I divide this by 2, I have 8 zeros and a 1. So what you got to think about is just what, like what is that number? So you just got to convert it to the appropriate hexadecimal value. And here, this is a 0001. This is a lots of zeros, 80. So you know these numbers ahead of time. You can figure out what that number is. And then in your code, I have the exact same code here, except that before I do the shift, I add this magic value. In this case, Q78, the smallest number I can represent is 1 over 256. Well, I add a value of 1 over 512. Well, if you work that on hex, that's what 1 over 512 is in a Q15.16 format. All right? So you just do this add. Now, the good news is all this stuff is known ahead of time. All right? This is something you know as you're writing the code ahead of time. So you can just go ahead and figure these numbers out. This is not necessarily dynamic. All right, and there it is. So that is a fairly advanced topic for the rounding. It's sometimes hard to kind of see what it is, but watch these videos a few times to really get this concept of rounding, because if you're trying to do high precision computation, you really should round before you truncate bits, because then it's a little bit more precise result. All right, lastly, we're just about done here, and I know that this is a very heavy topic, but in the end, it's just simple adds and multiplies and shifts. But one thing I want to show you is floating points versus fixed, kind of like graphically, of what they are. And so what I have here is an axis, a binary code. This is the number that would sit in like a variable register in the number we represent. What number we're actually trying to get. A pure integer, if we were to make this plot, the binary code versus the number you represent, we just get this straight line, all right? In the slope here is just 1. All right? Fixed point number systems, all we're doing here, and I'm just going to draw some endpoints. All we're doing with fixed point numbering systems is changing the slope of this line. So if we want, in this case, a wider dynamic range, meaning we want a bigger number represented, we choose a smaller scale factor, or I'm sorry, larger scale factor, so that we don't have quite as many digits of precision in the fraction, but we have a little bit more in the whole part. Or we can do this. And redraw this here. We can choose a scaling factor such that the values are max, the highest value we can ever get, and our lowest value we can ever get is smaller, but our slope is much smaller, or this 1 over n. We get a lot of precision from one number to the next. Here's the key part, is that any one number to the next number, it's always 1 over n, always. That's a really important thing, because we can really control error. Now, a floating point number, and I'm going to kind of draw this with a highlighter. Actually, let me just grab this gray color here. Kind of looks like this. Oop, let me do this. Sorry, this is hard for me to draw. A floating point number it's essentially a 2 to the n type curve, or 2 to the x. The binary code you put in the number, or the binary code you use to represent, when it translates the number represented, we have like a 2 to the x function. So on any one point here, and I'll pick a point here, for small perturbations, it's linear. Your error from one number to the next number is fixed for small changes. But for large changes over this curve, the distance from one number to the next number is not constant. It's changing. And the problem you get is, even though a floating point number, can represent really big or really small numbers, is if you're trying to add small numbers, say here, to a large number, this small number, is going to get, quite a bit of it's going to get blown away. So the problem is, when you're trying to do precision signal processing, that's very, very bad, because your error is floating around. What's really nice about fixed point, I can always limit my error to 1 over n. I can always do it. So for certain types of filters, say an IIR filter, an infinite impulse response filter, that has the possibility of positive feedback, we can better control what are called poles and zeros, and we can ensure stability. I've seen filters with floating point implementations that even they figured out the right form to put it in, direct form 2 or whatever, that they can have goofy noise artifacts because of this fact that a float, the error is not constant, over the curve, or fixed it is. So now, lastly, some challenges you have with fixed point numbers. We have C data types, all right? Those are 8, 16, 32-bit, 64-bit numbers, all right? You don't have to use those. You could use like a C struct to represent other data types to extend precision, but you need to write special functions to multiply and add them, and that can create a problem. Probably, this is a real hang-up, is that with fixed point, whenever you're working with the data in your actual code, you don't see the fraction in your compiler. You see the whole integer part. C does not have built-in fixed point support, and it makes sense why, because we can choose oddball scaling factors, and it's all up to the user. Where floating point numbers, the number format's fixed. You have to write custom routines if you want to output to a screen. Like, say, example, printf doesn't understand fixed point. So oftentimes, this is where floating point comes in handy. If you just want to print an approximation of your number, you can do that. Now, you can use the C preprocessor to help you. So, for example, if you want to get a number in Q78 format, I could define a macro that takes in a float, multiplies it by 256, and then converts it to a short. In that way, I could use the preprocessor to do the double precision floating point math to get my fixed point number. All right, and for debugging purposes, that can be useful. Now, it turns out you don't even have to do that. You can come up with other ways of getting your fixed point number and coming up with a base 10 what it is, and base 10 representation. But that seems to be a challenge. Now, I know some debuggers now, for example, CodeWarrior, Freescale's CodeWarrior, in the debugger, you can tell variable types what Q number format you want, and it'll just show you what it is. So that does make things, a little better. But that's a challenge, and between that and understanding what data types you have, and when you can have a possibility of an overflow and truncation, that's kind of like, overflow is the worst thing that happens in fixed point numbers, because that just totally blows away your numbers or your signal. So, parting thoughts. All right, fixed point numbers are very fast. They're all integer operations. That's a big deal. Some CPUs have built-in hardware to accelerate the shifting, the multiplying, And they may have very large accumulators, so you don't overflow. All right. Fixed point numbers can be used for very precise applications because the error can be controlled. It can be constant over the whole range of the format. All right. Some financial software uses fixed point to minimize error. Once again, because you think about numbering, representing numbers in a global economy. You want to keep track of cents, but you also want to deal with trillions of dollars. Like a 32-bit floating point number, even a double is not sufficient for doing that. You can make a fixed point, a binary, or even a scaled by 10 or 100 fixed point number and use integers. Once again, the biggest problem is overflow and saturation. This is when you run out of bits, all right? Your numbers get big enough where you run out of bits and you're kind of dealing with this these intermediate results. This requires you to keep track of overflow. So this can be a challenge. With floating point, you don't necessarily do that because the dynamic range is large. Some tool chains have nice libraries, but you have to understand your math problem you're trying to solve, and once you do that, it's not too bad. All right? You can use fixed point without a library. As you see, it's easy. It's just multiply and adds. You just keep track of the decimal point. Now, for example, ARM has a DSP library, the Simsys DSP, that it's optimized in a fixed point form for their processors. And in another video, we're going to look at their number format, and it turns out they use Q31. They have no bits of whole part. It's all in the fraction. You're thinking, why would I ever want to do that? It turns out that's a very smart thing to do for signal processing. And you might ask, well, what if I want a number bigger than 1 or multiply by a number bigger than 1? Well, it turns out that's pretty easy to do with some simple bit shifting. But you don't need a library. It's actually pretty simple to do it yourself. The only reason libraries come in is that if you're trying to optimize to use instructions built into the compiler, or built into the processor, a library may have inline assembly to take advantage of some fancy instructions that the compiler might already not already give you. So in terms of resources, I find like the Wikipedia articles are excellent on Q number format binary scaling. This reference is good from Randy Yates, but it is a fairly mathy approach. I tried to take a little bit different approach and look at things a little bit more qualitatively. Now, I'm going to say where I learned fixed point numbers is I used to be really into game programming, old 8 and 16-bit game programming. Older games needed really quick math. The best resources for fixed point numbers, I think, are looking up like old game programming reference material, because they didn't have floating point units and they had to do magical things. And even some of fairly recent game systems still use fixed point for speed. So I really like those as references because they had to squeeze as much as they can out of a processor without a floating point unit, and it was kind of amazing what they could do. So I hope this video series was helpful. This last one is a little long, but this should give you enough information now that you can handle fixed point numbers and kind of use them for yourself. All right, so see you later.